Okay, so we've got Whitney, Maddie, and iPhone. Who's iPhone? Ah, okay. All right, so we're going to go ahead and start section 3.3 today. So this is about power functions and polynomial functions. So we'll start with the, that's
I have
fine.
I have a quick question.
Uh-huh.
Is there any way that like for the next exam that you could give us, like not necessarily for points, but like questions out of the book to do like to practice for the exam? Because I feel like, especially for the last section of the last exam, none of the problems from the My Open Math homework were like at all related to how the problems were done on the like on the exam itself.
Sure, I can do that. Yeah, and like I said, it's mostly going to be problems from each section. So, up to, like I said, on some of them, don't go past 30 because then it get really, really nasty or whatever. And so that's going to be kind of like what it is on this one. It's going to be, whatever most of if you do the odds or even try the evens, you won't know if you got the evens right, but if you try all the odds on most sections or look at least some of each section, that'll be kind of more what it is. And it's usually the ones, what I do is I pick even ones out of each section to do for in class, and then so any of them that are left over from there might be options is kind of the key things. So, but yeah, I can give you some practice ones to do before the next exam.
Okay, that'd be cool. It just sometimes the ones on My Open Math are like completely unrelated to the way that you would do them. Cause like
Yeah.
on that one, like it didn't make us ever really solve the bottom portion of the like fraction thing, you know
Right,
what I mean?
right.
Like it would do it for you every
Yeah,
time, which
yeah,
made it kind of suck, I
yeah,
guess.
yeah, and that's kind of a bad thing. And after I've used this more on this my open math, I'm not sure I'm going to do that next time. I'm just going to say assign all the odds basically, and or however many, 1 through 33 or whatever, and say those are the ones to do, and but they're not going to be graded. The only thing will be there'll be quizzes instead. That'll be kind of like what we're doing for the test. So I'm going to change it because, like, so everybody said, "Oh yeah, that mom really works well," but then it doesn't really match what I want to test on. So
Hmm,
that's kind of the problem. So
cool. Thank
yeah.
you.
Hey, has Ben there with you?
I don't know where Ben is.
Oh, okay.
Oh, I think he forgot that he had class. He was at work doing work stuff.
Oh,
So
okay.
he's on his way.
Oh, okay. All right. Well, let's go ahead and continue then. So again, we're doing power functions and polynomial functions. So we'll start with the power functions. Once we get those, then we'll move over to the polynomials. So what is a power function exactly? Well, a function with a single term that is a product of some real number, a coefficient basically, and a variable raised to a fixed real number. So, we can use any coefficient k, so it can be positive, negative, fractions, decimals, whatever, and then times the variable which we're going to have as x. You can use r or t or whatever variable you want, it doesn't matter. Then raised to some power, some fixed number. So that's going to be the way a power function is. And those fixed p's, they can be, fractions, or they can be whole numbers, negatives, or whatever. And so that's what we're going to be looking at for power functions. And so what I did was I listed a whole bunch that were in the book, plus I did some more kind of at the bottom here. And so how do you identify a power function really? So what we have here is f of x equals 1. Is that a power function? Well, what could we rewrite that to fit this form kx to the power p? Well, we could say that's 1 times x to the 0. And so our p is 0 in this case, our k is 1. And so that does fit a power function. Okay, well, x, that kind of is just like, what this one is, except we have 1 times x raised to the power 1. So, that's power function. The 2, that's obvious. 3 is pretty obvious. Now, 1 over x, that makes it not quite so obvious because you haven't gotten the form x to some power. So what we have to do is we have to flip it over and say that's x to the negative 1, and it's still times 1. And that is a power function. And again, our variables are raised to any fixed real number. So as long as it's a real number, that works. And negative 1 is a real number. And so the same kind of thing works here with x squared on the bottom. When we take it to the top, that's x to the -2. And so that makes that a power function as well. Now the square root of x in the form here, it doesn't look like a power function, but if we say, well, that's x to the 1/2, then it's a form k times the variable raised to some power. And same with x to the third here, the square root or the cube root of x, that's x to the 1/3. Now the next one is the first one that we run into that's not a power function. That's because our base here is not a variable. It's 5, and it's raised to some variable power x, and the power has to be a fixed power, and that's not fixed, and the base here has to be a variable, and so basically those are swapped, and so that's not a power function. Now this one here, we have pi r squared. Well, r is going to be our variable, and it's raised to a fixed power 2, and it's times k, which in this case is pi. So that does fit the power function format. Now this one, we have two terms basically multiplied together. Well, as they are, that doesn't look like a power function, but if you actually multiply them, 2 times 4 gives us 8, and then x squared times x cubed, that's going to give us x to the 5th. And so now we have the k times a variable raised to some fixed power, and so that is a power function. So sometimes you have to simplify to be able to see the power function, and then you can see it a lot easier that way. Now the next one, we have three terms. They don't have the same exponents, so therefore we can't add them together and subtract them. And so therefore this is not a power function. In fact, this is going to be a polynomial function once we get to that. And then our last one, we have an x squared raised to the power of 3. And again, in this format, it's not a power function as we see it, with the kx to the p. And so if we go ahead and take 2 and raise it to the power of 3, that becomes x to the 6th, and we have a 1 still, and so that then is a power function. So sometimes the format they give it to you in is not the format that you can see if it's a power function or not. So simplify it down as much as possible, and then, if you have a radical sign, take it to the whatever power it is. If this is a 7, then take x to the 1/7, and then we have that fixed power of 1/7. So then it is a power function. So that's kind of some ways you can identify power functions. Now, what we're really interested in is, since this graph's about graphing and things like that, is going to be how do we identify the end behavior of these power functions? So what does it look like at the end of the power functions? And so for functions of the same family, what we can do is we can get a generalized view. And so what I went to do is I put it in Desmos, and I put in a whole bunch of values. So when we have on the left here, what we have is x to some n power, where n is even. And so, you could have x squared, x to the 4th, x to the 6th, x to the 8th. And basically what happens is your first one here, the red, is going to be x squared. And then the blue one that comes next, that's going to be x to the 4th. And then looks like green is next after that. And then purple's after that. What happens is the higher the power you go, the flatter it gets on the bottom. But all of those all behave the same way. All x to the n power where n is even all look like this. And so that's pretty much a generalized view. We understand how they're all going to work no matter where, as long as n is even, and our number out in front, in this case 1 times x to the n, is going to be positive, then this is how it's going to look. Now, if we have a negative out in front instead, what happens is it flips it over the x-axis, and now they go down instead of up, but they all are still the same kind of thing. They're all generalized. They all form the same looking um, shape, and so we can get a general view of that. Now the same thing happens if we look at odds. Odds are going to be, now it's going to do something like this for the regular x to the n, where starting with n is 3, we get the red one. So it has not much flatness here. Then as we keep going and get more and more higher powers that are odd, it gets flatter and flatter here right at this base. And then when we get negative x to the n, where we get the odd, and it flips over the y-axis now. So what happens is now this flips over here, and this part flips over here. Now we have something that looks like this. And again, it still flattens out here. So it's all generalized the same way for odd powers of n when you have that negative k here. So what we can do is we can make a general table here, and this is actually a table out of your book, and I wanted to kind of show you it really does, all follow this way, whether you have just the 3 or you have 3, 5, 7, 9, and so on as you go up. And so if we have a positive k, basically anything k greater than 0, and we have an even power, it's going to look like this. And so what happens is, as x goes to negative infinity, y, or f of x, if you want to look at it as f of x, goes to positive infinity. And as x here goes to positive infinity, f of x or y goes to positive infinity. Now, if we have the negative constant, so that's a negative x to some n power that's even, then it's going to go down like this. And so as we go x to negative infinity, our f of x is going to go to negative infinity. And over here, as we go positive infinity for x, we're going to go still negative infinity for f of x. Now, when we have odd powers, basically, we are seeing that as you go to the negative infinity, the f of x is going to go to negative infinity. And as you go to positive infinity for x, your f of x is going to go to positive infinity. And then the kind of the opposite here, as we go to negative infinity for x on the negative k, then it's going to go to positive infinity for f of x. And as we go to positive infinity for x, it's going to go to negative infinity for f of x. And so these are kind of the generalized things. And really all we're looking at is that end behavior here. So we really are just looking at what really happens at these tips where the arrows are. And so that's kind of the key thing is what happens, at this point, at this point and at this point, and then here, what happens down here, and then at this one, we have the opposite. So that's really all we're looking for here is what happens at those endpoints. So what we want to do is be able to look at any value or any power function and say, okay, what is our end behavior for the given power function? Well, here we have x to the 12th. So here what we know is, we know that, if I can find my thing, n is even. And so, we're going to have basically some kind of a function that's going to be, now here we also need to know what k is. Well, k is greater than 0. So that means it's probably going to be really some flat thing that looks like that, but it's going to have going up here, it's going to go up here. So basically, um, let's see, as x approaches negative infinity, f of x is going to approach positive infinity, because as we go this way, it's going to go up. And then as x approaches positive infinity, f of x is also going to approach positive infinity. So the key is knowing that, the k and n, basically you have to know those if they're odd or even, and then what the k value is. And then you can draw the general function, and then you can get the general things here, which is, as x goes one direction, you get y goes to the other direction, and so on. All right, so let's look at the second one here. We're going to, again, might be easiest just to draw. So here we know n is odd, and k is going to be less than 0. All right, well, being odd normally would come and go like this, but because we have that negative, it's going to come down, it's going to be flat, and then it's going to go like that. And so our general function then at the end behavior is, as x goes to negative infinity, as we go to the left, then f of x, or y, is going to go to positive infinity. As we move to the right, as x goes to positive infinity, f of x is going to go to negative infinity. And so the key thing is knowing those 4 different directions, all these 4 here. And with that, we can come up with just giving us the x to the 12th or minus x to the 13th, we can come up with a general formula. Now, we might not have exactly how flat it is here drawn out perfectly, but we know what those end behaviors are. And that's really the key, is what is the end behavior. Okay. All right, so that's power functions. Now, polynomial functions, they're a little bit different. They're kind of like a polynomial. You know, we have some x cubed minus 4x squared plus 3x minus 2, something like that. And so basically, it's going to equal either 0 or finite sum of non-zero terms. And it's going to be written, you know, a sub n x to the n plus da 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 all the way down to a sub 2 x squared plus a1 x plus a0. So basically, you're going to have some normal function that we always see. So, you know, it might be our f of x equals 3x to the fourth minus 4x cubed plus 2x squared minus x plus 4, something like that. It's going to be a form like that. And n is the non-negative integer of the power. And so that's going to be our highest degree. And then we're going to have some coefficient here, and that's going to be any real number. But the only key is that number has to be not equal to 0, because if that's equal to 0, then that n is not going to be the highest n, it's going to be the next one down. And then again, if you have that cannot equal 0, otherwise it would still be, you know, not working. And so always whatever your n is for the highest degree, that leading term or leading coefficient here has to be equal to something besides 0. Okay, and each term here is basically a term of the polynomial. So this one has 1, 2, 3, 4, 5 terms to it. You know, some of them are going to have 2 terms, some are going to have 3 terms. It just depends on the polynomial itself. So looking at these 6 examples here we have x minus x to the fourth. Well, we could rewrite that as x to the fourth minus x to the fourth rather plus x, and then that kind of fits more along the lines of what we have there, and so that is going to be a polynomial. Now the next one basically is a factored form of a polynomial. So if we went and squared x minus 1, then took that times x plus 2, and then took that times 2x, that would give us a polynomial. And it's going to be of degree, well, here's going to give us a degree of 2, and another one is 3, and another one's going to be 4. So it's going to be some polynomial with the x to the fourth in it. So our n is going to be 4. Okay, and our leading coefficient is going to be a 2. Other than that, the rest of it we'd have to multiply out to decide what it is. But we can get that far with just saying, okay, well, this squared is x squared, then times x is going to be x cubed, times 2x is going to give us 2x to the fourth. All right, so number 3 here, we have, again, now we have the base is 3. So already we don't have the right thing, because we have to have a variable there instead. And it's raised to some x plus 1, which is going to raise it to some, you know, variable integer. And so that one is not going to be. So it's kind of like the power function. You can't have a base of a number. You have to have a base of a variable raised to some number power. So that one is not going to be a polynomial. Now this next one, number 4, that's just in the normal form of polynomial. You know, you just have the highest power and then decreasing powers after that. And so that one is. Now this one, just 2x to the fourth. Well, you know, if we had some more terms here, yeah, that would be a polynomial. But as it is, that's really just a power function. We just have the one term. It's some variable to a power that's, you know, fixed, and we have a coefficient in front of it. So that's a power function. And this one here, x squared over x squared minus 1, well, that's not, because it doesn't really fit this format here that we're looking at. And so that's not going to be a polynomial, nor is it going to be a power function either. All right, so like we said, you know, polynomial function in general form is going to be basically written in descending powers of the variable. So for example, you know, if this was our function, that's written in descending powers, 4, then 3, then 2, then 1, and then there's going to be x to the 0. Now, this leading term is the first one basically with the highest power. And so this would be our leading term. Okay, and we kind of talked about this a little bit. And so from that leading term, we know that n is going to be the degree of the polynomial. So in this case, n is equal to 4. So that's the degree of the polynomial. And sometimes we also need the coefficient. So here the coefficient is equal to 2. And that's because that's going to tell us, you know, if we had an even, then that's going to be the general shape of it. And that's also going to say that k is going to be greater than 0 and n is even. Now, if we had something like this, that was going to tell us n is even and k is less than 0. So both of those are very important. We need to know the degrees and we need to know what that coefficient is because that's going to depend on how the shape of the graph is. If it was odd, then it's going to come down, then do that. And if that's going to be k greater than 0, otherwise it's going to come down and go like that if k is less than 0. So those are the key things that we need to know, and we can get it from the polynomial itself. Now, the key thing is with polynomials, they work the same way as with power functions. So we don't have to memorize anything different. If we know the degree and we know the coefficient, the polynomials follow the same end behavior. Now, what goes on in between, that's going to be totally different. So it might, come down here and come down here, but a polynomial might do something like this depending on what degree it is. And so you might have a lot of stuff in between, and we don't know what that part is, but we know that end behavior, which is the key thing, and we just get that from our degree and our coefficient. So with this one, determine the end behavior. Okay, well, what do we have? N is equal to 4, so it's even. So we know it's going to be, either like this or like this, depending on what our coefficient is. Our coefficient k is equal to a -2, so that's less than 0. So what that means is this is going to be what our end behavior is. And so, as x goes to -infinity, f of x goes to -infinity. And here, as x goes to +infinity, f of x also goes to -infinity. Okay, so that's kind of following in behavior, and all that comes from is that first leading term. Now you have to be careful sometimes. They'll put the polynomial in funny order and it won't be always the general form. It'll maybe be, they could have put -3x squared, then minus 2x to the fourth, minus 1 plus x, and you'd have to rewrite it and get it in the right form, and then you could find your leading term very easily. Now this one, here again, we have n is even, so n is equal to 2, but this time k is greater than 0, so then we have the top case, we have something like this, and so then we say as x goes to -infinity, f of x is going to go to +infinity because it's going to go up. And then here, as x goes to +infinity, f of x is also going to go to +infinity. Okay, and so knowing that in behavior, again, we don't know what happens here, but we know what happens there and there. And in this case, we know what happens here and here. We don't know what happens in the middle, but we do know what happens on those end pieces. All right, so here, what about this one? Well, here we'd actually have to multiply it back out. We'd have to take the x squared times this, times this, times this, or since we know that this is the highest term, the 3, and this is the highest term, if we take this times this, that's going to give us 2x to the 5th. That's our leading term. We're done. Now we can figure out what the end behavior is. Well, this is odd. So because it's odd, and here k is greater than 0, so k is greater than 0, and we have n is equal to 5, which is odd, then we have something that looks like that. And it's going to be really more flat here because we do have that n is greater than 3 basically. And so the 3 would have came down and just kind of been a more curved, but these are still smooth curves. There's no edges where it goes and has a 90-degree corner or anything. It's all smooth. And so we know then our ending things is as x goes to -infinity, f of x is going to go to -infinity. And as x goes to +infinity, f of x is also going to go to +infinity because that's the points we know on the end. Again, we don't know what happens in the middle here, but we do know what happens on those ends. Now this one, we really don't want to multiply all that out 7 times. So what do we have to do? Well, really all we have to think about is we have a negative x, we're raising it to the power 7. So really, if you think about that, what we have is negative x plus 2 times negative x plus 2 7 times. And so if we take that negative x times negative x times negative x 7 times, that's going to give us a negative x to the 7th. Well, here, n is equal to 7. That's odd. And k is less than 0. So what happens is we're going to have something that looks more like that. Again, all we're worried about at this point is those ending things. What's going on in here, we don't know and we don't care at this point. We're going to figure that in a little while. But right now, ending behavior is all we're worried about. And so as x goes to here, negative infinity, f of x goes to positive infinity. And as x, lost my arrow there, goes to positive infinity, f of x goes to negative infinity. Okay, and so we know how the ending behavior is on both of those just because we know how the general shape of the graph is. All right, so this time they give us a graph and they want us to kind of what is the ending behavior and what is the degree of the function or the possible degree of the function. All right, so what do we know? So on the first one here, it looks like we have is n is going to be even because we have this, parabola. And we know that k is going to be less than 0 because it's kind of going down. And so what do we know from there? Well, we know that the end behavior is basically as x goes to negative infinity, the y goes to negative infinity as well. And here as x goes to positive infinity, then the f of x or y goes to negative infinity. So we can see that just based on the graph, because this is just going to continue on this direction, and this one's just going to continue on that direction. So we know basically in behavior, just this is where it goes, this is where it goes. And the degree of the function, well, the minimum degree, so if we want the minimum, that's going to be 2. Now, do I believe that that's actually going to be a 2? No, I think it's going to be higher, because what happens is this is going to be so flattened out. It's probably going to be a 4, maybe a 6, maybe an 8, but that minimum degree is going to be a 2, and that's all we really can determine at this point here. Now, what about this one? Well, here we know n is odd because we have this shape here like this. What else do we know? Well, we know k also in this case is going to be less than 0, because normally it would come down and then it would go over and come down again if it was positive, but it's negative, so it's going to go the opposite direction. So let's go ahead and erase my extra line there. And so we know that that's going to be a negative. So here, the minimum degree is going to be equal to 3. Okay. Now, do I believe it's going to be 3? No, it's probably going to be maybe 9, maybe, because it's really, really flat here. But at that point, we don't know what it is. But the minimum degree is going to be, our possible is 3. Okay. All right, so here what we have is we have local behavior. And so local behavior of polynomial functions basically is going to tell us where are the turning points. And so, what's happening, on these, we didn't know what's in that square. We don't know what's going on. We just know the end behavior. So now we're going to kind of start looking at what's going on in between there. And so what we're going to find out are, how many turning points, where it goes from positive to negative or negative to positive, increasing or decreasing. And we can also learn our x and y intercepts, what's crossing the line, what's not crossing the line. And we can do this 2 different ways. First way is by factoring. And so that's going to be the most common. You're going to just, graph it or factor it, set those equal to 0, use zero product rule, and you're going to get your x-intercepts. You can get your y-intercept by plugging in y equals 0 and solving for x and getting that, and that's not going to be a problem. But factoring is going to be probably the hardest for people because we've forgotten how to factor. So if we look at this, what do we factor out of here? Well, we can see that 2 is common to all of them and x is common to all of them. So let's factor out a 2x. So what's left? X squared. Factor out a 2 here, that's going to be a minus 3x. Factor out a 2x here, that's going to be minus 10. Okay. Now, can we factor the trinomial? Well, let's see. If we have 2x, then we have x and x. One's going to be plus, one's going to be minus. The two factors of 10 that add to 3, well, that's going to be a 5 and a 2. And the 5 has to be negative. It's bigger, and our middle term is negative, so that has to be negative. That has to be positive. So that's going to tell us the factored form. So we're going to have this is a factored form. And from this, what we can say is set each of those terms, 1, 2, 3, equal to 0. So if we do that, the first one says x is equal to 0. The next one says x is equal to a negative 2. And the last one says x is equal to a positive 5. So if we want to write our intercepts or wherever it hits, that's going to be 0, 0. That's going to be a negative 2, 0. And that's going to be a 5, 0. Okay. Now, if we plugged in y equals 0, or the y equals 0, that's also going to give us 0, 0. So that's going to be not only an x-intercept, it's also going to be the y-intercept. Okay. So those are intercepts. How many turning points and what are the turning points going to be? Well, that would be kind of requiring a calculator, but we know our intercepts. And so if we had to, we could graph that much. But what I want to do now is do a different share here and try to do the calculator. All right. And what we're going to do is we're going to find intercepts by graphing. And so what I need to do is I need to remember that last equation, which was 2x to the third. And then it was a minus 6x squared. And then minus 20x. And so my graph, oh, looks nice. So that's my graph. And from this, I really can't tell what it is, but there's going to be an easy way to do this. And that was kind of what was on the screen there. And what we can do is we can find our first intercept, the y-intercept, and that's going to be x equals 0, 0. That's where it crosses the y-axis. And so that one they give you, you don't have to do anything. You just have to hit trace and enter, and it gives you the intercept. Now, if we want to find what these 3 x-intercepts are, if that wasn't, say, a y-intercept, say if it was somewhere else, we have to hit the second trace. And then we want 2, we want the 0, so we want to find the x-intercept. And so now what we have to do is we have to set our left bound. So let's say that's our first left bound. Now we need to set the right bound, which is going to be to the right of where it crosses. We set that. And then the guess, you can just kind of backspace and say, okay, that's where I guess. Then it says minus 2, 0. And if you remember, one of our factored forms was the x equals negative 2, so that would be minus 2, 0. Now we know the next one is 0, 0, so we can skip that one. So let's do a second trace, number 2 again. Now let's look at that far one. All right, so that's going to be our left bound because it's asking what is their left bound. So we want to go from here somewhere past that point. And so now our guess, well, I'm guessing it's going to be there. And this one actually is nice because it gives you its 5, 0. But now it tells us exactly that that 0 is 5, 0. Okay, so now we've got our zeros through our calculator instead of graphing. So sometimes you need to know how to do the graphing and be able to find your zeros on the calculator. Okay, so now we knew the end behavior. We knew it was going down to negative infinity. It was going up to positive infinity. But now we actually see what our middle part is. So we're increasing from here. We hit that point there and we start decreasing. And then at that point, we start increasing again. So we turn 2 times. There's 2 turning points. We have 1, 2, 3 x-intercepts. And so that tells us a lot about that function. And so let me go back to this. And so this is kind of what I was doing there. If you want the y-intercept, you hit trace and then 0 and enter. And then if you want the x-intercept, you hit second calc. And then you have to find your left bound, your right bound, and then arrow close to where your guess is and enter, and it tells you the intercept that way. And so that's how we do it calculator based. Otherwise, we just do the factoring. And so when I was talking about those turning points, those were the two turning points. We had that one that was going up and then one that was coming down. Those were two turning points. We found our, three intercepts, the three x intercepts, and then the one, which is also the y-intercept. And we got all of that just from our equation of the polynomial. All right, so the next one, let's do that one also with factoring as well as with the calculator. So this one, it looks like I can factor out a -2. And I want to usually have a positive highest n-terminal value for factoring just to make it easier. So if I factor out a -2, that becomes 6n squared, then plus n, and then -1, okay? Now, how do I factor that? Well, that's going to be a -2 times. Well, usually I want to factor that into the two different terms, 2n and 3n. Now I want a positive in the middle, and that's going to be a negative. So basically, the highest one needs to be positive. So I want a +1 and a -1, because if I do that 3 times, that's going to be a +3. Then that's going to be a -2, then a -n. So that looks like my factored form. Now, when I set that equal to 0, it's nothing. And so if I set this equal to 0, I get n is equal to too many things down at the bottom here. Okay, we'll write it over here. N is equal to a -1/2, and on the second one we get n is equal to a positive 1/3. And so that gives me a -1/2 0 intercept, and this one gives me the 1/3 0 intercept. Okay, so those are my intercepts for that. Now if I plug in 0 here for the n and 0 here, I get 0, 2 for my y-intercept. So these are x-intercepts, and that's the y-intercept. And we can do the same thing with our calculator. We have to go up here. Let's clear that. Now we type in our equation again. And now this time I forgot to write it down. So it was, I think, -12x squared. And then what was it? +2x. And then -2, maybe? I don't remember. Hopefully that was what it was. Let me go look real quick. 2 -2 + 2. What did I write? -2 + 2. Okay, so -2 + 2. All right. All right, so my graph looks like I need to change my window. Let's say we have maybe all right, so that looks like probably what it's, I don't know, that doesn't look right, but let me plot on my other calculator on my thing here. All right, y equals, All right, so that looks good. It's good enough for what we need anyway. So now we need to get those trace values. So that one, we just hit trace. We see our intercept 0, 2, which is what we knew. Now we can hit second trace and get our x values. So our left one, let's start there. Move to the right. That looks like it's beyond it. So let's that. And this time I'm not going to guess. I'm just going to have that. And we get negative 1/2, 0, which is what we found on one of them. Now let's do our second one. Let's do that as our left bound. That's our right bound. And here, that one we have to know that 0.3333 is 1/3, so 1/3 0, which is what we found as well. So that's how we can use our calculator to do the same thing we did with just the factoring. All right. So some extra details about functions, polynomial functions. So to be continuous, we need a continuous function. That basically means there's no breaks in the graph. So you can basically draw the whole graph without lifting your pen up. And it also has to be smooth, so there's no sharp corners. So some of my corners look kind of sharp, but they're actually they're just all round corners. There's no actual 90-degree points. It all is just a smooth going from left to right on the whole graph. All right. Then we have our intercepts and turning points, which we've been kind of looking at. Now, the key is now they're going to tell us, okay, well, the polynomial of degree n, so whatever our highest degree is going to have at most n x-intercepts. So if we have something x to the fourth, that means we're going to have at most 4 intercepts that are x's. And we're going to have n minus 1 turning points. So 4 minus 1, which would be 3 turning points. So that we're getting a little more fine detail of what kind of happens in between our extreme behavior at both ends. And so what we can do is determine basically the maximum number of x-intercepts and the turning points without graphing. And what we do is, again, we first have to figure out what is our degree of the polynomial, and then we take n minus 1, and that tells us the turning points. Because we know if n, that's the intercepts, n minus 1 is turning points. So this one is one of those that's not written in general form, and so we have to look and see which is the highest degree. Well, the highest degree is this term here. So n is equal to 12. I'm not going to rewrite the whole thing. I'm just going to look at it and say, okay, n is equal to 12. So that means I have at most 12 x-intercepts. And then I have 12 minus 1, or 11 turning points. Okay, and that's just from this equation, knowing that the highest power is going to be my n, and so that's going to be n is equal to the most number of x-intercepts there is possible, and n minus 1 is the most number of turning points. So again, looking at the next one, again, they don't put it in the right order, and so this really should be our leading term and leading coefficient. And so here n is equal to 3, so we have at most 3 x-intercepts, and then that gives us 2 turning points. Okay. So that's another thing that we can use eventually to help us draw these graphs of the function, just given the function and without actually using our calculator. So that's going to be something that's going to be useful here for the next pieces. So what we're going to do now is use what we just learned, that n is the most number of x-intercepts and n minus 1 is the turning points, to kind of look at the graph now and go backwards. Okay. So what can we tell about this graph? Well, remember, we have the possibilities. We have, like this, that's even, and k is greater than 0. We have this one where it's even and k is less than 0. We have this one, which is odd, and k is greater than 0. And we have this one, which is odd, and k is less than 0. All right. So what do we have here? Well, we have something that looks like more like this last one. It's odd, and k is less than 0. So what generalizations can we say? Well, we know it's going to be an odd degree. Now there's turning points. Well, there's 1, 2 turning points. And there's 1, 2, 3 x-intercepts. Okay. So the best thing we can guess on this here for the best generalization is the degree of the polynomial is going to be equal to a minimum of 3, because we know we have 3 intercepts and 2 turning points. And so this is usually n, this is n minus 1 if at the minimum. And so then I'm going to say that this is a degree 3 polynomial. Okay. Now this one, a little bit different. Here we're going up here, up here. Well, which one goes up and up? Well, that's going to be even and k greater than 0. So we can say it's even degree. You know, k is greater than 0. And so what can we get from this? Well, we know we have 1, 2 intercepts. How many turning points? We have 1 turning point, 2 turning points, 3 turning points. And we know that that's equal to n minus 1. So if that was n minus 1, if we add one more, that would give us 4 as the degree. And that's most likely what it is, because here we only have 2 intercepts, but we have to have n greater than the turning points by 1. And so since that's an even degree, 1 more than the 3, that's going to give us, it's a degree 4. There's 3 turning points, 2 x-intercepts, and just the stuff we could get directly from the graph. It's an even, and k is greater than 0. All right, what about this one? Well, here we're going up on the right and down on the left. So that looks to be the odd k greater than 0. So it's going to be odd degree when we get done, and k is greater than 0. Now here we just have one x-intercept. Okay. Well, how many turning points do we have? We have one turning point there, one there, one there, one there. So we have 1, 2, 3, 4 turning points. All right. So that means if we have n minus 1 of that, we add one more to that, that means our degree in this case is probably 5, because one more than that would give us 5, and that's going to be an odd degree, which fits the actual format of the polynomial as far as going up and down on the left and right. And so I would say it's degree 5, 4 turning points, and the coefficient is greater than 0. Okay. And so that's kind of all the different things we can get out of just the graph itself so far. All right, so what can we do now with these graphs? Well, let's say, what are they? Are they actually a polynomial? Because sometimes you'll get a graph, it might not be a polynomial. Sometimes it might be. And so what we have to be able to do is recognize if a graph is a polynomial. Well, here, if we look at this, this fits kind of the typical odd function. This one looks like 2 turning points. And so, yes, I would say that is a polynomial. And it's of odd degree, and k is going to be greater than 0. Okay, and the possibility of the degree, well, if there's 2 turning points, that means n minus 1 is equal to that. So n then is going to be a degree of 3, which fits this polynomial, because it's odd, which is what we knew it had to be, and it has to be at least, n plus the n minus 1, so that's 2 plus 1, so that gives us a 3 for our degree. What about 2 here? Is that a polynomial? Well, if we look at that, it's not a polynomial, because it doesn't really fit anything, because what happens is this goes closer and closer to 0, but it never reaches it, and then this goes to infinity, so it doesn't fit any of our possible endpoint things that we know about. We'll draw, there we go. So it doesn't fit any of those, and so that is not a polynomial. Okay. Well, what about this one, number 3? Well, it looks fine. It looks like it's going to be an odd polynomial, but these red lines indicate that we don't go past that point. And so what do we know about the domain of a function? The domain is all real numbers. And if it's all real numbers, then it's saying, well, we're limited to, going from, I don't know, whatever this is to this point, and everything is everything in here, but nothing out here. That means that this is not going to be a polynomial either, because we have to have a polynomial be all possible x values. It can't just say, okay, it can only go from -2 to +2 and everything in between there, but nothing beyond. So that is not going to be a polynomial. Now this one's kind of drawn how I end up drawing graphs. That has a square corner, and so that's not a smooth continuous function, and so this is not going to be a polynomial either because it's not smooth. And so the polynomial function has to be smooth. As you can see, that's nice and smooth. This one's nice and smooth too, but it's limited where our x values are, so that makes it a not one. But if it hadn't been limited, then that would be kind of smooth as well. So we have to have that really key feature of its being smooth to be a polynomial function as well. All right, so those are kind of the key things in this section that we can do with polynomial functions, with graphs, and things like that. And so what we're going to do now is we're going to expand our stuff to moving to application problems, which is everybody's favorite, I know. All right, so this one says an oil slick is expanding as a circle. The radius of the circle is increasing at the rate of 20 meters per day. Express the area of a circle as a function of d, which is days. And so that's what we need to do. Well, what do we know about a circle? Well, the circle, we need to know the area is equal to pi r squared, okay? And what do we know about anything? Well, we know the radius is increasing by 20 meters per day. So if we write a function for that, the radius, and we're going to, as a function, it's going to be as a function of days, well, that's going to be every day is going to be an extra 20 meters. So it's going to be 20 times however many days it is. So if it's day 1, it's increased by 20 meters. If it's day 2, it's increased by 40, and so on. And so that's going to be our function for the radius. Now we need to plug that into a function for area. Well, what do we know about area? Well, we're just going to say, well, area, and it needs to be in terms of days again, because that's what it really is asking for. And that's going to be pi times the radius, which is 20d squared. So basically we had to figure out what is our function for the radius in terms of days, and then plug that into area. Now we have to square that. Well, that's going to be 20 times 20. That's going to give us 400. And then we still have pi, and then now we have d squared. Okay, and so instead of having r squared, it's going to be based on d squared, the number of days squared, and so that's going to be our area. Now it doesn't tell us, what is the area after 7 days or anything. It just says find the area of a circle as a function, and so that then is what they're asking for. The area of the circle as a function of days is just going to be 4 squared. Okay. All right, so the next it's going to be something like this. And it says it has a length of 10 inches and a width of 6 inches. Okay, well, length is 10 inches, the width is 6 inches. Now, if the length is increased by x inches and the width increased by twice that amount, express the area of the rectangle as a function of x. All right, well, area is just length times width. So what we said was the length is increased by x inches. So if we say a of x, because we're going to be adding x to it, we're adding x here, And the width increased by twice that amount. So that's going to be increased by 2x. And so 10 plus x times 6. And so that's going to be all of it. Now we have to FOIL. So now we just take first times that, second times that, second times that. And so we get a equals, that looks like 60 plus 20x plus 6x plus 2x squared after we do all those. Now, if we write that in the general form, that's going to give us a of x equals, now we need to bring the 2x squared first. And then 20x plus 6x is 26x, then plus 60. And so that's going to give us the area of the rectangle as a function of x. And so basically it started out as L times W. Well, we 10 and 6 initially, and then it increased by x for the length and 2x by the width. And then when we plugged that in here, multiplied it out, and simplified into the general form, we ended up with that. Okay. So again, all these are basically trying to remember, area is length times width, or area is pi r squared. All right, so one last one. So here it says a rectangle is twice as long as it is wide. The squares of side 2 feet are cut out. Squares of sides, size, that's supposed to be size. That doesn't make sense. That's a S or a Z rather. Spelling check works really good. Of size 2 feet are cut out from each corner, then the sides are folded up to make an open box. Express the volume of the box as a function of the width. All right, so let's draw our box first. All right. So the rectangle is twice as long as it is wide. So if we say this is x, that's 2x. And we're cutting out squares with each side being 2 feet long out of each corner. So that's 2, 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 and that's 2. So we're cutting out those squares on each side. Now is when you have to kind of imagine what we've done here. So basically, if we do this, this piece is gone, this piece is gone, this piece is gone, and this piece is gone. So what we have is this here piece, this here piece, this, and what we're going to do is we're going to fold it into a box. So this piece we're going to fold up, we're going to fold that up, we're going to fold that up, and we're going to fold that up. And so when we look at it from a side view, that's what it's going to look like. And since these were each 2, that's going to be, the height is 2. So that's going to be our height. Now, depending on if we're looking at this end or if we're looking at this end, depends on what this is. So if we're looking at it one way, that's a 2x. But if we look at it the other way, then that's going to be just x. Okay. So thinking about the box now, if I can draw this in 3D. Something like that. And it's open on the top, so we don't have anything there, but we have a height of 2. That's going to be our 2x. That's going to be our x. So we have height, we have the width, and we have the length. So that's what's happened. When we cut those out, we folded those up, and we have a box that kind of looks like that. So looking at one end, we have something that we can see there. The other end, we have that. And if we remember a volume of, in this case, it's going to be like a cube or a rectangle, is going to be length times width times height. So volume is going to be equal to, and this is in terms of x because we've cut out x, or we have x as part of our variable here. So how long is the width now? Well, it's going to be x. Then we have 2 off here and 2 off here. So what's that going to be? Well, that's going to be x minus 4. So better write all our pieces here. So height we know is 2. Then we have x minus 4 is going to be this one. And this one's going to be 2x, then minus 4. Okay. And I guess I forgot to write those on there because I was just thinking of the actual initial widths and lengths. Okay, so we really have to cut that out. And so really the distance is 2x minus 4. And here it's the x minus 4. So I need to write that properly. And so we just take and multiply all that together. So first I'm going to FOIL. And so x times that's going to give me 2x squared. X times that's going to be minus 4x. Then minus 8x plus 16. And then that's still all times 2. And that's 2x squared minus 12x plus 16 times 2. So that's 4x squared minus 24x plus 32. And that's the volume of x. And so that's going to be our volume of our basically our rectangular box after we took out these 2x2 corners on each one and folded them up. Okay. So any questions there? All right, so that finishes 3.3, and then tomorrow we'll look into 3.4.